Hey there everybody, I'm going to power through a bunch of examples of U substitution in order to make an integral that is somewhat complicated, less complicated, and therefore easier to solve. So I'll just go as quickly as I can and see how many examples we'll get to. What the game is we're playing is it's all about finding a part of your mixed up function that contains the derivative of another part. So as you look at this, we know that when we take a derivative of something, it will go down by a degree if it's a polynomial. And in this case, if I make my substitution be this part, then when I take the derivative, I will incorporate that derivative into this and thereby eliminate it and make it simpler. So for example, if I let u be equal to x to the third plus 1, then when I take the derivative of that, I will get 3x squared, that goes to 0, and then dx. Don't forget the dx part. And I've got x squared dx, so I need to get rid of that 3, so if I just multiply each side by 1/3, 1/3 of du is equal to x squared dx. So this part here then will be equal to this part, and then this part here just goes down in there. So this then becomes the integral of the square root of u and then du, but don't forget that 1/3, which we can pull out front. But this is a lot simpler than the previous x version to integrate. Okay, so what's going on here? I'm looking at this. Sometimes it can be confusing at first, but if I see this 1 over x, and I remember that that's just x to the minus 1, when I take the derivative of that, I will get 1 over x squared, or I'll get x to the minus 2. Don't worry about multipliers like numbers out in front. Don't worry about pluses and minus signs, because we can easily adjust for that. So I let u then be equal to 1 over x, which is x to the minus 1. Easy to use the power rule then. Du is minus x to the minus 2 dx, and then that's equal to, you can write it as minus like dx over x to the second if you want, and you'll see there that is, and there that is, and then I will just take this u and put it in there. So this becomes then the integral of u then times du, but don't forget the minus sign out front. So that's going to be that. Next one, same thing, only different. This is very simple. But again, you just want to not think of it as like the sign. Think of it as the part that when I take the derivative of that, I will find that part later. So u equals x squared, du equals 2x dx. So then I know that 1/2 du equals x dx. There's my x dx part. So again, this then is just equal to the integral of the sine of u du with the 1/2 out in front. Same thing here, except that when I take the derivative, I don't see a second part, except that remember there's going to be a little invisible 1 out there, and when I take the derivative of 3x, I'll get a constant, and I can adjust that constant down to 1. So my u then is going to be 3x plus 2. When all else fails, just try the thing inside the parentheses and see what happens. Du then is 3 dx, so 1/3 du equals dx. So now this then becomes the integral of u to the 2.4 power du, but then 1/3 out in front. All of these then are quite simple to do. This guy, again, what do you see that is going to crop up somewhere else? Well, in this case, this is the ln of x squared. So I know that the derivative, the ln of x, is 1 over x. So again, a lot of these jump out, and you'll see that if I let u be equal to the ln of x, then du equals 1 over x dx, and again, this becomes quite simply u du, and I'm good. U squared, just be careful you identify where it is that you're making that substitution. Again, Do I see something where I find the derivative again? Yes, that's the beauty of e to the x. So u equals e to the x, du equals e to the x dx. And again, there's my e to the x dx. So this then just becomes the integral of the cosine of u and then du. This guy down here, again, look at degree. This is a third degree polynomial. Don't be too freaked out by the constants there, a and b. They just represent constants. They're not like extra variables like x. If I take this inside and take the derivative of it, what's going to happen? When all else fails, you can just try something like this, plus bx to the third. When I take the derivative of that, what do I get? Oh yeah, I get 3a plus 3bx squared, which is equal to 3 times a plus bx squared. And that's all going to be then with the dx thrown in. Don't forget that. So then 1/3, we like taking thirds of things, this example set, a plus bx squared dx. So then I can say that that then is going to be equal to the integral of 1, this is going to be, sorry, this will be 1/3. I'll be able to get rid of all of this. 1/3, and then 1 over the square root of u du. All right, you see that? Because this whole thing is right here, and then the 1/3 I pulled out, and it's just 1 over the square root of that. Again, much easier to actually find the derivative or the integral of that. Okay, just a few more here. Again, I'm looking at a cubic or a squared term and a cubic term, so it makes sense that I try subbing in and going down to get rid of that. So u equals t to the third plus 3t, very similar to the last one, 3t squared plus 3t, again, factor out. We're going to have another third, that's t squared plus 1. Oh, that should have been just 3. And that gives me t squared plus 1. You'll catch yourself if you make a mistake like I just did, because you sort of know what the target is. And these are contrived often in a way to work out. So you should sort of expect things to work out. Don't forget the dt, in this case dt. And then again, I'm going to go 1/3 and just cross that out. So then this becomes, this, again, this whole thing here is being substituted here by this. So it's going to be 1/3, and then it's just going to be u to the 4th du. Okay, so again, much, much easier to integrate. Okay, now they're getting a little bit more complicated. So if I've got the cotangent of z under the square root, and this is cosecant, do you remember what's a relationship here where you're looking for something and then its derivative? Well, the derivative of the cotangent, the derivative of the tangent is secant squared, the derivative of the cotangent is cosecant squared, but minus, and that's dz. And so here I've got pretty straightforward. I'm just going to sneak it in down here. The integral then of the square root of u, and I'm going to pull out that minus, and then it's just du. Because this negative and the cosecant squared right there comes out. Again, secant and tangent, okay, a little bit more difficult here. You have to start thinking about what's the relationship between any of these. Well, if I take the derivative of the tangent, like I just said, I get the secant squared. So du is secant squared of x, then dx. And that's going to mean that then if I pull out and separate these into, oh, no, that's some little mistake there. I caught that. So this is, think of this as secant of x times secant tangent, secant x tangent of x. be careful which direction you're going. So you can see there that if I try to make this substitution, that's not helping me because I put tangent in there, and then I've got secant squared only, so that's going the wrong way. If you really think about what is the derivative of the secant of x, that's secant tangent, secant of x, tan of x. And that does help me because now what I've got is I've got secant squared times secant tangent, and I found this is the derivative part, and that's the original part. So you can see I jumped off to the wrong start, but then caught myself because the substitution didn't work, so I tried going in another direction. So this then becomes my u squared, then du. It's as simple as that. This one, again, I've got t and I've got t, so there's not a change in degree, so it's not like some of these earlier ones like this one where it goes from 3 to 2. But what I'll try here is I'll try just using u equals 2t plus 5. It makes sense that you try the thing inside the parentheses that's sort of being complicated by that degree. And then if I do du, I get 2 dt. That's not helping me that much, but if I take and rewrite this so that I take away 5 and divide by 2, I've got t is equal to u minus 5 over 2. And now I can substitute this in a way that I can apply my exponent rules and make it somewhat easier. So this becomes then the t, I replace the t with what's equal to. I'm just going to go u minus 5 and pull the 1/2 out. And then my t, and then my parentheses going to the 8th power is just going to be u to the 8th, and then I'm going to go du like that. And now you can see what I'll get then is 1/2 u to the 9th minus 5u to the 8th du, and this I can do much more easily.